In this video, we'll be discussing bounded and monotone sequences. Now, it's important to note that in Calculus 2, there's an important theorem that specifies that every bounded and monotone sequence will converge. So, for us to be able to utilize this theorem, we're going to have to first define what bounded and monotone functions or sequences are. Let's start off with monotone. A monotone sequence is specifically a sequence such that it is either non-increasing or non-decreasing. Now, throughout this video and lecture, I might end up reusing these words. Instead of saying non-increasing, I might emphasize that it's always decreasing. Now, this is not necessarily always true, because a non-increasing function can also retain a concept of constantness. Okay, so it might actually approach something that is more constant, such that it's going 1, 1, 1, 1, 1, which we do know is going to be a converging sequence. However, the reason why we're concerned in terms of it being non-increasing is simply that it's not going to bounce around at all. It will always decrease or be constant. So again, if I use the phrase always decreasing, or again, in vice versa, for non-decreasing, always increasing, we should imply that we are also inferring that it might also be constant at certain points. So, a monotone sequence is simply a sequence that is either always increasing, or constant, or always decreasing. Again, simply not doing the other thing. Now, after we've identified that, it's important for us to look at a sequence. So let's look at this sequence here. And again, we talked about this in a previous video of a geometric. This is nothing more than a geometric sequence. Is this geometric sequence monotone? And the answer is yes. If I were to try and plug in some of these values, again, if I plug in 1 and then 2 and then 3, this is 1, so this is 1/2, so about here, and about here, you'll notice that this function right here, all these terms, all these sequential values, they are always decreasing. So I would call this sequence monotone. And again, we'd have to make some kind of clarification as to why it's always non-increasing. There are ways that we can do that effectively. We're not going to go ahead and show that in this particular case, but in other cases it does come up and we can utilize it. It is always, again, monotone, in this case, non-increasing. So the fact that it's non-increasing provides us with some extra ability to determine what's going to happen next. So after I've identified it being monotone and non-increasing, the next thing I have to work with is whether or not it's bounded. And again, I'll abbreviate bounded as BDD. So we can either specify that the sequence is bounded above or bounded below. What's important to note in terms of bounded above or bounded below is that it must be used in accordance with monotone in a specific way. So for instance, if this thing is monotone non-increasing, then I know it's bounded above. It's not really that important or impressive that I can say, hey, guess what? This sequence, it's bounded above by 1. I mean, yeah, sure, we can say it's bounded above by 1. Heck, we can even say it's bounded above by 1/2. We can say this because no other values will be larger than a 1/2 value, and 1/2 is the bound. It does obtain that value. It's okay that it obtains that value, but no other value will be above that. That doesn't really help us. And the important reason why that doesn't really help us is because if I have a non-increasing sequence, then this thing might be decreasing uncontrollably, continuing on down forever. I don't want a non-increasing bounded above. I want non-increasing corresponding with bounded below. So I want to be able to come up with a rule as to why that this particular sequence is then bounded below. Well, if I look at this thing right here, I'll know mathematically that every value I plug in, it'll be 1/2 to the power of that number. Is there any number that I can plug in that will provide me with an overall value as a term as a negative number? And the answer is no. So when we look at this, I can argue that it's bounded above, sure, by 1/2. And then I could also say that it's bounded below. And the reason why, again, the logic works, it's bounded below by, well, I could use, say, like -1, because I know that this thing is never going to obtain negative values. So the fact that I can use -1 provides me with some kind of justification as to it being bounded below. But a more appropriate answer would probably be bounded below by 0. Again, because I can't obtain a negative number, I can't obtain any negative number, which means that bounded below by 0 is a more reasonable option. Now, with this being done, I have a sub n equals 1/2 to the power of n is a bounded, non-increasing sequence. If it's bounded, sequence, and if it's bounded and monotone, then that means that a sub n will then converge. Now, I don't really need to use bounded and monotone theorem on this particular sequence. Again, if a sub n is equal to 1/2 to the power of n, then I could just go ahead and straight up take the limit of it. The limit as n goes to infinity of 1/2 to the power of n, I can manipulate this to be the limit as n goes to infinity of 1 to the power of n divided by 2 to the power of n, because I can distribute powers over division. This is then equal to the limit as n goes to infinity of 1 divided by 2 to the n. Again, 1 to the power of any number will be 1. So 1 over 2 to the n will actually approach 1 over, well, 2 to the n goes to infinity as n gets larger, which means this is going to go to 0. So we don't need to use bounded monotone sequences to determine that this particular geometric sequence will converge. It's very clear that this converges to 0. If you recall from the last video in terms of geometric sequences, this should have converged to 0 from the beginning. Now, with all that being said, this is great and dandy. It doesn't help us with this sequence, but it does help us with other sequences. For instance, this sequence right here, again, we can claim will converge by using limits. However, if I were to look at a sequence that looks like this, you might look at this and say, well, that doesn't necessarily converge. I can't easily take the limit of both sides of this. Because for me to be able to take the limit of both sides, I need to know what this side does and what this side does. I need to know that these terms, a sub n and a sub n plus 1, are both going to approach a number, and I can't just randomly assume that those two values will be the same. I don't know that this thing's not going to bounce back and forth. I don't know that this thing's not going to continue on towards infinity or negative infinity. So what I'm going to do first is I'm going to go ahead and talk about, again, bounded and monotone. So, with bounded, I can argue that as, I'm sorry, I need a sub 1 here, don't I? I'm going to go ahead and start with a sub 1 is equal to, let's do 3, okay? In this case, let's talk about bounded. If I plug in 3 to this, my first term is 3, my second term would be 1. If I plug in another value, say the 1 goes in next, I'm going to have 1/3. And I can argue that this thing is bounded above, specifically above, by 3. And then below, could I say that it's bounded below by some value? Well, again, if I wanted to, I could go ahead and create a number of different terms, or I could understand and recognize that as I plug numbers in, once again, this thing will never be negative. So it's bounded below by 0. The next detail is monotone. As I plug in 3 and then 1 and then so on and so forth and getting more and more values, I'll recognize that the values are never actually increasing. Again, more importantly, it is retaining either a decreasing personality or it is remaining constant throughout the values. In that case, this is monotone, again, non-increasing. Now, I don't necessarily have to talk about the above by 3. That's not actually that important, but we've been able to do it. I know that it's non-increasing and then therefore bounded by 0 below. These two pieces together tell me that it's bounded and monotone. Again, non-increasing and bounded above doesn't help me. If it was non-decreasing and bounded above by 3, then we could say something. In this case, given that it's bounded below by 0 and non-increasing, I know that this sequence, a sub n plus 1 equals to 1/3 a sub n, will converge. If I know that it will converge, well then I can say that the limit as n goes to infinity of a sub n, or the limit as n goes to infinity of a sub n plus 1, will both equal to some number. We're going to call that number L. Now the reason why we're allowed to do this is because, again, if a sub n plus 1 will converge, that means that a sub n will converge. Both of those numbers should approach the same number. So if we identify that they're both L, then this sequence is no longer a sequence. I mean, it still is. But now we can replace a sub n plus 1 with L and a sub n with L. Now, to be honest, we're not actually replacing them with L. What we're doing is we're taking the limit on both sides. We're taking the limit as n approaches infinity of this side, and we're taking the limit as n approaches infinity of this side. Now, the limit as n approaches infinity of this side right here becomes that L, and over here, the 1/3 can be pulled out of the limit because it's a constant value, and it's the limit as n goes to infinity of a sub n becomes L. You'll notice here then that I could go ahead and solve this particular equation, meaning L minus 1/3 L equals to 0, therefore 2/3 L equals to 0, therefore L equals, well, if I multiply both sides by 3 and then divide both sides by 2, 0. So I'm not saying that L is 0, I'm not saying that a sub n is 0, I'm not saying that a sub n plus 1 is 0, I'm saying that the limit as n approaches infinity of a sub n plus 1 equals to 0. Hence, this is a bounded function, non-increasing, and I can guarantee by the bounded monotone theorem that a sub n will approach L, as will a sub n plus 1. I can replace those values in the rule here such that this, I'm taking the limit of both sides, replacing this and this a sub n with L. I'm going to go ahead and create a equation, and I'll be able to solve for L. Now, some of you might have realized at the beginning of this section that this right here is nothing more than a recurrence or recursive formula for a geometric sequence. It's important to understand that this does work for other sequences if we can guarantee bounded and monotone.